What would happen if the limits we believe to be the greatest in the universe are, in truth, only the central portion of something far more expansive? For many years, humanity looked up at the sky and believed it had grasped the shape of the largest galaxies. And then, from old data quietly forgotten in radio archives, an immense structure slowly emerged. Not brilliant, not dramatic, simply stretching in silence across tens of millions of light years. If this stirs your curiosity, leave a comment, tap like, share this episode, and subscribe to the channel to join a community of contemplative listeners stepping more deeply into the stillness of the universe. For now, allow yourself to relax and prepare to enter the journey that follows. It did not appear as a sudden discovery, nor as a bright announcement written across the sky. Instead, Alcyoneus emerged in a quieter way, through careful attention to signals that had already been recorded and set aside, waiting without urgency inside archives of radio data. For years, those radio observations had mapped the northern sky in broad strokes. They showed familiar patterns: compact galaxies, modest radio lobes, shapes that fit comfortably within existing expectations. Nothing seemed out of place. And yet, within those same maps, something vast extended beyond the edges of what earlier surveys were designed to capture. The outer regions simply fell outside the frame, trimmed away not by choice, but by technical limits. In a sense, Alcyoneus had been present all along. Its central region appeared ordinary enough, and so the larger structure remained unnoticed, not hidden by darkness, but by perspective. When astronomers returned to the data with wider fields of view and greater sensitivity, the picture slowly expanded. What once seemed complete revealed itself as only a small portion of something far larger. One might imagine standing partway up a mountain slope, surrounded by trees and rock, seeing texture and detail close at hand, while missing the full outline of the mountain itself. Earlier radio surveys were much like that vantage point. They captured the center, the brightest emissions, the regions easiest to detect. Beyond them, the signal continued, faint but persistent, stretching far past what had been expected. As the wider structure came into view, its scale began to register. On either side of the host galaxy, enormous lobes of radio emission extended outward, formed by streams of energetic particles moving through intergalactic space. Each lobe reached for millions of light years, until together they spanned a distance of roughly 16 million light years from end to end. The number itself matters less than what it represents, a structure so large that familiar galactic comparisons begin to lose their grounding. Placed beside the Milky Way, which spans on the order of 100,000 light years, the contrast becomes difficult to hold in a single image. One could imagine lining up more than 100 Milky Ways end to end, yet even that picture remains incomplete, because Alcyoneus is not a solid disk, but a diffuse, elongated presence woven into the space between galaxies. Scale like this does not announce itself with brightness or noise. These radio lobes are faint, detectable only at low radio frequencies, where delicate instruments can trace the glow of electrons spiraling through magnetic fields. The light we see is not starlight, but synchrotron radiation, a quiet marker of motion and energy spread thinly across immense distances. The recognition of this size did not arrive as a dramatic moment, but as a gradual realization that the measurements continued to exceed familiar boundaries. Earlier records for the largest known radio galaxies began to feel provisional. Alcyoneus did not compete with them. It simply extended beyond, calmly, without alteration to its appearance. The observation came through the low-frequency array, known as LOFAR, a distributed network of radio antennas spread across Europe. Rather than a single dish, it operates as a coordinated system, combining signals from many locations to form a telescope with extraordinary reach. Its strength lies not in magnification, but in sensitivity to low-frequency emissions that other instruments often overlook. By tuning into frequencies between roughly 100 and a few hundred megahertz, LOFAR listens to a part of the spectrum where ancient, expanded radio structures remain visible. It was here that the full extent of Alcyoneus became clear. its lobes tracing paths through the intergalactic medium like distant echoes of activity long past. What made this realization more striking was how unremarkable the galaxy at the center appeared when viewed in visible light. Through optical telescopes, the host galaxy looks like a faint elliptical system, neither especially bright nor unusually massive. Its central black hole, while large by everyday standards, falls well within known ranges. Its stellar mass does not set records. Nothing about the visible core alone would suggest the ability to shape space across such extraordinary distances. There are no obvious signs of violent mergers or extreme densities that might immediately explain the scale of the radio structure. In visible wavelengths, Alcyoneus blends quietly into its surrounding. Only when the radio view is overlaid does the full form emerge. From that modest core, narrow jets once streamed outward, feeding the enormous lobes over long spans of cosmic time. The contrast between the calm appearance of the galaxy and the vastness of its radio extensions invites a broader view, one that looks beyond internal properties and toward the environment through which those jets traveled. This quiet mismatch hints at influences operating on scales larger than any single galaxy. The surrounding intergalactic medium, the density of matter along cosmic filaments, and the relative emptiness of the region all play roles in allowing such structures to grow and persist. In sparse environments, radio lobes can expand with little resistance, carrying energy far from their source before fading. Seen this way, Alcyoneus is not only a story about size, but about context. Its discovery reflects how the universe often reveals its extremes, not through dramatic events, but through careful adjustments in how we look. By widening the frame, by listening at different frequencies, familiar skies can take on unfamiliar dimensions. The radio light we detect today left those lobes millions of years ago. What we observe is not a current state, but a memory preserved in electromagnetic form, stretched across space and time. The structure may have evolved since then, changed in ways we cannot yet see, continuing its quiet interaction with the surrounding cosmos. As attention settles on this immense figure traced faintly across the sky, it becomes part of a broader landscape of large galaxies and extended structures. Nearby in thought, though distant in space, are other giants, shaped by different histories and environments. The sense of scale established here does not conclude anything. It simply adjusts our orientation, opening outward toward comparisons yet to come, where Alcyoneus will be placed alongside another immense presence, and the quiet patterns of the cosmic web will begin to take shape around them. Long before Alcyoneus quietly entered the picture, attention rested on a different kind of giant, one whose presence felt more familiar, more aligned with how galaxies had long been defined and measured. IC 1101 did not announce itself through faint radio outlines or distant lobes stretching into emptiness. It stood out through mass, concentration, and an overwhelming abundance of stars gathered into a single, immense form. IC 1101 lies more than 1 billion light-years away, embedded at the very heart of the Abell 2029 galaxy cluster. From that central position, it dominates its surroundings, not through motion or brightness, but through scale and gravity. In visible light, it appears as a vast elliptical glow, smooth and uniform, without spiral arms or sharp internal features. Its light carries a warm, yellow tone shaped by stars that formed long ago and have been slowly aging ever since. Seen from afar, the galaxy resembles a luminous sphere with softened edges, its boundaries fading gradually into the surrounding space. There is no clear point where it ends. Instead, its stellar envelope thins almost imperceptibly, blending into the diffuse light of the cluster itself. This quality made IC 1101 a defining example of what astronomers once considered the largest possible galaxy. Measured through classical optical methods, its diameter reaches several million light-years, already far beyond the scale of galaxies like the Milky Way. Its mass in stars is even more striking, estimated to be on the order of 100 trillion stars, gathered through countless mergers over cosmic time. This accumulation, often described as galactic cannibalism, unfolds slowly within dense clusters, where large galaxies gradually absorb smaller companions that drift too close. For decades, IC 1101 held a quiet place at the top of size charts. It appeared in textbooks and surveys as a natural upper limit, a practical boundary that models of galaxy formation could accommodate, if only just, in this sense, it became a reference point, not because it was dramatic, but because it seemed to fit within an expanded version of established rules. The arrival of Alcyoneus changed that sense of stability, though not by contradicting IC 1101 directly. Instead, it exposed a deeper uncertainty, one that had always been present but rarely addressed. The question was no longer which galaxy was larger, but how that question should be asked at all. Size, in astronomy, is not a single measure. It depends on what is being counted and where boundaries are drawn. If one measures a galaxy by the spread of its stars, IC 1101 remains unmatched, its stellar halo extending farther than almost any other known system. If one measures by radio emission, tracing the reach of energetic particles far beyond the visible galaxy, Alcyoneus occupies a very different category. The contrast is similar to measuring a city. One approach counts only the dense urban core, where buildings cluster tightly together. Another includes the suburbs, the highways, the extended networks that connect distant neighborhoods into a functional whole. Both measurements describe the same city, yet yield vastly different scales. Galaxies present the same challenge. Their stars form a bright core, but they are surrounded by extended halos of dark matter, faint stellar light, hot gas, and, in some cases, radio-emitting plasma that travels far beyond the visible structure. Each layer fades gradually rather than ending abruptly, making any definition of an edge feel provisional. IC 1101 excels in one domain. Its stellar mass and smooth envelope represent the extreme outcome of long-term growth within a rich cluster environment. Alcyoneus excels in another, with radio lobes that trace the influence of its central black hole across distances that stars themselves never reach. Neither measurement is incorrect. They simply describe different aspects of what galaxies can become. What unites these two systems is not competition, but tension with existing models. In simulations of cosmic evolution, galaxies as large as IC 1101 appear rarely, forming only under specific conditions over long spans of time. Structures like Alcyoneus, with radio extensions of such scale, are even less common, sometimes absent altogether. This does not imply that something has gone wrong. Instead, it suggests that the universe occasionally explores the far edges of possibility, producing outcomes that sit near the limits of prediction. In probabilistic terms, these galaxies occupy the thin tails of distribution curves, where rare combinations of environment, timing, and energy align. IC 1101's growth reflects the quiet persistence of gravity over billions of years, gathering stars into an ever-expanding envelope. Alcyoneus reflects the ability of black hole activity to imprint structure far beyond the visible galaxy, interacting with the intergalactic medium along paths shaped by cosmic filaments and dark matter halos. The recognition of Alcyoneus did not erase IC 1101's significance. Instead, it reframed it. What once seemed like a final benchmark now appears as one expression among several, each highlighting a different way galaxies occupy space. The notion of a single largest galaxy begins to dissolve, replaced by a spectrum of extremes shaped by distinct processes. Scientific records adjusted quietly, without urgency. Reference lists expanded. Diagrams stretched. The change did not feel like an overturning, but like a widening. An acknowledgement that earlier boundaries had been drawn conservatively based on what instruments could reveal at the time. Both galaxies remain distant and unchanged by our classifications. Their light continues traveling toward us, carrying information from the past rather than the present. What we see now reflects stages that may no longer exist, preserved through light travel time as a kind of cosmic memory. As attention shifts between stellar mass and radio extent, between visible envelopes and invisible halos, the idea of scale itself becomes more fluid. The universe does not insist on tidy categories. It allows structures to grow in different directions, under different rules, often at the same time. In this widening perspective, IC 1101 and Alcyonius no longer stand as rivals. They become markers along a broader continuum, guiding attention outward toward the environments that shape them, the cosmic web that connects them, and the quiet forces that set limits on how large such structures can grow as the universe continues to expand. At this point, the figures attached to galaxies like IC 1101 and Alcyonius have already drifted far beyond everyday experience, settling into a realm where numbers alone no longer offer much guidance. Lengths measured in millions of light-years, masses counted in trillions of stars, and time spans that stretch across most of Earth's history all exist comfortably on paper, yet remain strangely resistant to intuition. One way this gap reveals itself is through comparison. When astronomers attempt to translate cosmic distances into familiar scales, the intent is not precision, but orientation. Imagine the Milky Way reduced to the size of a small coin resting in the palm of your hand. On that scale, Alcyonius would extend far beyond it, longer than several football fields laid end to end, not as a solid shape, but as a faint, elongated presence stretching across open space. In another analogy, the sun becomes a grain of sand. With that change alone, the Milky Way expands into something closer to the span of a continent. IC 1101, under the same transformation, grows even further, spreading outward until it covers an area comparable to the surface of the Earth itself. These images do not make the universe smaller. They simply allow the body and mind to briefly sense proportion, before that sense dissolves again. What becomes clear is not how large these galaxies are, but how quickly human intuition gives way. Distances increase by factors so large that comparison stops functioning as a tool for understanding and becomes instead a reminder of scale itself. The universe does not compress neatly into metaphors. It allows them only as momentary bridges. Distance, however, is only one part of the picture. In astronomy, every distance is also a measure of time. Light does not arrive instantly. It moves at a finite speed, carrying information slowly across space. Inside Alcyonius alone, light takes around 16 million years to travel from one end of its radio structure to the other. Within IC 1101, even crossing the luminous stellar envelope requires millions of years. To put this into perspective, much of Earth's biological history unfolds during such journeys. While a photon begins its path from the outskirts of one of these galaxies, life on Earth passes through countless stages of change. Species appear and vanish. Landscapes reshape. Civilizations rise and dissolve. By the time that same photon completes its passage across a single galactic structure, the planet receiving it may no longer resemble the one it left behind. This means that size measurements are never just spatial, they are temporal. Every boundary traced across a galaxy also marks a deep reach into the past. Observing the width of Alcyonius is not simply observing length, but observing how long energy has been traveling through space, uninterrupted, across vast intervals of cosmic time. When we observe IC 1101, whose light has been traveling for roughly 1 billion years, we see it as it was long before complex life appeared on Earth. Alcyonius, even farther away, reaches us from a time when the universe itself was noticeably younger. The images and data arriving now are records, not updates. In this sense, astronomical observation resembles the viewing of very old recordings. What plays before us is real, but delayed. The structures existed, the light was emitted, the radio waves propagated outward, all long before any observer was present to receive them. The universe performs continuously, but we arrive late to every scene. Because of this delay, distant galaxies appear almost like lingering impressions. They persist in our instruments as patterns of light and radio emission. Even though their current states remain unknown, some may have changed significantly. Others may have faded or transformed in ways we cannot yet detect. The signal does not inform us of the present. It offers a preserved moment. This is why astronomical catalogues always contain a quiet uncertainty. Labels such as largest or most massive apply only to what has been observed within a specific window of time and distance. They describe what appears largest in the record available to us, not what exists at this exact moment across the universe. Seen this way, the cosmos becomes layered with delayed information. Each galaxy occupies a different temporal depth, depending on how far away it is. Nearby systems show relatively recent states. Distant ones reveal conditions from much earlier eras. The sky is not a snapshot, but a mosaic, assembled from many different times at once. Alcyoneus and IC 1101, despite their immense size, participate in this same pattern. Their apparent dominance is framed entirely by observation delay. What we measure now is not an absolute ranking, but a reflection captured through light that has been traveling for hundreds of millions or billions of years. This delay does not weaken astronomical knowledge. Instead, it defines it. By comparing galaxies across distances, astronomers reconstruct a sequence, assembling a broader narrative of how structures form, grow, and interact with their environments. The past becomes a guide to understanding long-term behavior, even when the present remains inaccessible. As attention rests on these immense systems, the awareness of time deepens. The universe does not reveal itself all at once. It arrives in layers, each one shaped by distance, motion, and expansion. What appears solid and defined is, in fact, a memory carried forward at the speed of light. Within this quiet framework, scale becomes something felt rather than resolved. Distances stretch intuition. Time dissolves familiar reference points. Galaxies take on the character of long-lasting traces rather than fixed objects. They exist, they evolve, and they continue interacting with their surroundings, even as their images linger far behind. From here, the view naturally widens. Individual giants like IC 1101 and Alcyoneus begin to feel less isolated, more connected to the larger patterns of matter and space that guide their growth. Beyond their visible outlines lie filaments, voids, and flows that shape how energy and material move across the universe, extending the story outward without pause. Within the broad outline of IC 1101, attention can rest for a while on what fills its volume, not as a dense accumulation, but as a vast arrangement of stars spread across an almost unimaginable span. Estimates suggest that this single galaxy contains on the order of 100 trillion stars, a number that resists any attempt at direct counting or full comprehension. If one were to count steadily, one number each second, the process would continue for millions of years without reaching the end. Even that image only gestures toward the scale involved. These stars are not packed tightly together. They are distributed through an enormous halo, extending outward for millions of light years, their combined light forming the smooth, golden glow seen in optical images. Most of these stars formed early in the universe's history, more than 7 billion years ago. Their light reflects advanced age rather than ongoing creation. Cooler, longer-lived stars dominate, giving IC 1101 its characteristic yellow and orange tones. Regions of blue, associated with newly formed stars, are scarce. The galaxy has long since passed its most active period of star formation. This pattern places IC 1101 inches, a late phase of galactic evolution. Growth now proceeds slowly, shaped less by new stars than by gradual interactions within its cluster environment. Smaller galaxies that pass nearby may still be absorbed, adding to the total mass, but the internal character remains largely unchanged. At the center of this vast system lies a feature that sets IC 1101 apart, even among giant ellipticals. its core. The luminous central region spans more than 10,000 light-years, larger than many entire dwarf galaxies. Yet this core is not densely packed. Instead, it shows a surprisingly low concentration of stars, spread across a wide volume. This unusual structure is often interpreted as a record of past mergers over time, as massive galaxies combined within the Abell 2029 cluster. Their central black holes likely followed inward paths of their own. When such black holes formed pairs and eventually merged, their gravitational influence altered stellar orbits nearby, redistributing stars outward and leaving behind a broad, diffuse core. Rather than a compact nucleus, the center of IC 1101 appears expanded and thinned, carrying the imprint of these long-past events. The result is a core that feels spacious rather than crowded, shaped by dynamics unfolding over billions of years. Embedded within this region is the galaxy's central black hole, whose estimated mass lies in the range of tens of billions of solar masses. This places it among the most massive known, approaching the upper bounds suggested by current models of black hole growth. Such an object influences its surroundings through gravity alone, without spectacle. Its event horizon spans a region larger than the orbit of Pluto, yet remains small compared to the galaxy as a whole. Matter, drifting too close, contributes to a slow inflow, releasing energy that interacts with the surrounding gas rather than producing dramatic displays. The existence of black holes of this scale raises open questions. Their growth likely involved repeated mergers, sustained accretion over long periods, and favorable environmental conditions within dense clusters. Each of these factors plays a role, though no single explanation fully accounts for the largest examples observed. Beyond the stars and black hole, IC 1101 is permeated by a hot, diffuse medium of gas. This plasma reaches temperatures of tens of millions of degrees and emits strongly in X-rays. Though extremely sparse, it fills the space between stars and extends throughout the galaxy and into the surrounding cluster. In visible light, this gas remains invisible. If observed through X-ray instruments, however, the region around IC 1101 appears bright and expansive, tracing the distribution of energetic material shaped by mergers, stellar remnants, and feedback from the central black hole. This hot environment plays a quiet but decisive role. Gas at such high temperatures does not readily cool and collapse to form new stars. Instead, it remains suspended, preventing the galaxy from renewing its stellar population. The result is a stable, slowly evolving system, where change occurs on very long timescales. Despite the immense number of stars, most of the galaxy's volume is nearly empty. Average densities are far lower than even the best artificial vacuums created on Earth. The distance between neighboring stars is so great that direct encounters are extraordinarily rare. The galaxy's size arises not from compactness, but from arrangement. If stars were scaled down to the size of basketballs, the nearest neighbor would lie thousands of kilometers away. This emptiness is not incidental. It allows the structure to remain extended without internal disruption, permitting gravity to shape form without forcing collapse. IC 1101 demonstrates that a galaxy's grandeur does not come from solidity, but from balance. Mass, motion, and space coexist in proportions that allow vast systems to persist for billions of years. The galaxy holds together not by filling space, but by organizing it. Seen as a whole, IC 1101 becomes less an object and more a landscape, one defined by age, distance, and slow change. Its stars trace an early chapter of cosmic history. Its core records ancient mergers. Its black hole and hot gas continue to influence the environment quietly, without urgency. This interior view does not resolve questions about how such systems form or where their limits lie. Instead, it adds texture to the broader picture, showing how extreme size can emerge through accumulation, dispersion, and time. As attention gradually shifts outward again, away from the inner structure and toward the larger surroundings. IC 1000. 101 begins to feel inseparable from its environment. Its scale reflects not only what it contains, but where it resides, within a web of matter extending far beyond any single galaxy, carrying the story onward without pause. At the heart of Alcyoneus lies a system that does not announce itself through brightness or visible form, yet shapes regions of space far beyond the galaxy's stars. Its influence begins close to a central black hole and extends outward through processes that unfold steadily. Guided by gravity, rotation, and magnetic order, matter drifting toward the black hole does not fall straight inward. Instead, it gathers into a rotating accretion disk, spreading into a flattened structure where gas and dust circle at increasing speeds. Friction and compression raise temperatures dramatically. At these extremes, atoms lose their electrons, and the material becomes plasma, glowing across a wide range of wavelengths, from radio waves to X-rays. This rotating disk functions as a converter. Gravitational energy is transformed into motion and radiation, not through sudden events, but through continuous circulation. Most of the material gradually spirals inward, crossing the event horizon. A smaller fraction is redirected outward, channeled into narrow streams aligned with the black hole's rotation axis. The energy that powers these streams does not come from chemical reactions or explosive processes. It arises from gravity and spin. As the black hole rotates, it drags nearby spacetime along with it. Magnetic fields anchored in the surrounding plasma become twisted by this rotation, storing energy in their configuration. This arrangement gives rise to what is known as the Blandford-Znajek mechanism. In this process, magnetic fields extract rotational energy from the black hole itself. Plasma is accelerated along the field lines and expelled in two opposing jets, moving at speeds approaching that of light. Near the center, these jets remain narrow and focused, guided by magnetic tension and rotational symmetry. Rather than dispersing immediately, the jets maintain their direction over immense distances. They travel outward through the intergalactic medium, carrying energy far beyond the visible boundaries of the host galaxy. Along the way, interactions with surrounding matter gradually slow the flow, and the jets widen, transitioning into expansive radio-emitting lobes. In Alcyoneus, these lobes extend for millions of light-years on either side, together spanning a distance of roughly 16 million light-years. They are not solid structures, but regions where energetic electrons spiral through weak magnetic fields. As they do so, they emit synchrotron radiation, most visible at low radio frequencies. To radio telescopes like the Low-Frequency Array, these lobes appear as faint, elongated clouds, tracing the accumulated history of jet activity over long spans of time. Their visibility depends not on density, but on persistence. The jets must have remained active and aligned for hundreds of millions of years to produce structures of such scale. The magnetic fields involved change character with distance. Near the black hole, their strength is extreme. Farther out, within the radio lobes, they weaken to levels comparable to those found between galaxies. Even so, they remain sufficient to guide charged particles, preserving the overall shape of the lobes and preventing rapid dispersion. These magnetic structures act like invisible channels, directing plasma flow across vast regions of space. Without them, the jets would quickly lose coherence, spreading into the surrounding medium and fading. Instead, they retain a recognizable form, extending steadily outward, marking the path of energy transfer. Maintaining this configuration places demanding requirements on the system. The central black hole must be supplied with matter at a relatively steady rate for a very long time. Interruptions or changes in direction would leave observable signatures, bends, or breaks in the radio structure. In Alcyoneus, such disruptions are minimal. This suggests an environment that supports stability. The galaxy's position within the larger cosmic structure likely plays a role, allowing gas to flow inward along preferred paths. Rather than isolated activity, the jets may reflect a broader interaction between the galaxy and its surroundings. The total power involved is immense, comparable to the combined output of many millions of stars. Yet it is distributed across a volume so large that its effects are subtle rather than dramatic. the energy does not accumulate explosively. It diffuses, heats surrounding gas, and alters conditions over long timescales. Through this process, the black hole becomes more than a sink. It acts as a mediator between scales, linking the compact region near the event horizon to the intergalactic medium far beyond the galaxy. The radio lobes serve as a record of this connection, preserving the imprint of motion and alignment across cosmic distances. What makes Alcyoneus distinctive is not merely the presence of jets, but their endurance. Sustaining near light speed outflows over such durations challenges existing models. It points toward a balance between fuel supply, magnetic structure, and environmental conditions that is rarely achieved. This balance does not resolve into a single explanation. Instead, it invites attention to the broader setting in which Alcyoneus exists. The jets do not operate in isolation. They interact continuously with surrounding matter, shaped by density variations, large-scale flows, and the geometry of space itself. As the view expands beyond the radio lobes, the focus begins to shift away from the central engine and toward the larger framework that supports it. The question becomes less about how the jets form, and more about how the universe provides pathways for energy and matter to travel such extraordinary distances, carrying the story onward into the structure that connects galaxies to one another across the cosmic web. Beyond the boundaries of any single galaxy lies a structure that shapes them all. A framework so extended that individual systems appear as brief concentrations within it. On the largest scales, matter in the universe does not spread evenly. It gathers into an intricate arrangement often described as the cosmic web. A vast network that guides how galaxies form, move, and evolve over time. This web is composed of long filaments and broad walls of matter, intersecting at dense nodes and surrounding immense regions of relative emptiness. Most of its mass is invisible, carried by dark matter, which provides the gravitational scaffold upon which ordinary matter settles. Gas, stars, and galaxies trace these hidden structures, outlining paths that stretch across hundreds of millions of light-years. Seen in simulation, the cosmic web resembles an interconnected system of threads, where dense intersections become natural gathering points. Galaxies do not choose their locations freely. They emerge where matter flows converge, where gravity draws material inward along preferred directions. Over long spans of time, these locations become sites of sustained growth. IC 1101 occupies one of these favored positions. It sits at the center of the Abell 2029 galaxy cluster, a massive collection containing thousands of galaxies bound together by gravity. The cluster itself rests at a major node of the cosmic web, where multiple filaments meet and funnel matter inward. Within this environment, motion slows. Galaxies passing through the cluster gradually lose energy through interactions with the surrounding medium and with one another. Over time, many drift toward the center, drawn by the deep gravitational well. IC 1101 resides at the lowest point of this well, where incoming systems are most likely to arrive. As smaller galaxies approach, tidal forces begin to strip stars from their outer regions. Repeated encounters stretch and disperse them until their material becomes part of the larger system. This process unfolds gradually over billions of years, adding mass not through singular events, but through accumulation. The smooth, extended halo of IC 1101 reflects this long history of absorption. The effects are visible not only within the galaxy itself, but throughout the cluster. A significant fraction of the cluster's total light does not belong to any single galaxy. Instead, it comes from stars that now drift freely between systems, having been removed during past interactions. This intracluster light forms a faint, diffuse glow, detectable only through careful observation. These stars follow the cluster's gravitational field rather than the orbit of a particular galaxy. Their presence records earlier encounters, offering a quiet archive of motion and disruption. In clusters like Abell 2029, this diffuse component can account for a notable share of the total starlight, spreading across space without clear boundaries. Alcyoneus, while different in character, is shaped by the same larger framework. Rather than sitting at the center of a rich cluster, it lies along a filament of the cosmic web. These filaments act as channels through which gas and smaller galaxies move, guided toward larger structures. Along such a filament, matter flows continuously, not in a rush, but as a steady migration driven by gravity. For a galaxy positioned within this stream, material arrives from preferred directions, supplying gas over long periods. This arrangement may help explain how the central black hole of Alcyoneus remained active for such extended durations. Instead of relying on short-lived bursts of fuel, the galaxy appears to have access to a sustained supply, delivered by its location within the web. The jets that created its immense radio lobes may reflect not an exceptional black hole alone, but a favorable position within the universe's broader circulation of matter. In this sense, the cosmic web functions less as a static backdrop and more as a system of pathways. It connects galaxies across great distances, shaping their growth indirectly by controlling how material moves. The largest galaxies tend to occupy places where these pathways intersect or remain well-defined over time. Not all regions share this abundance. Between filaments lie vast voids, enormous volumes of space where matter is scarce and galaxies are few. Some of these voids span hundreds of millions of light years, containing only scattered systems separated by great distances. Within such regions, growth proceeds differently. Galaxies evolve in relative isolation, with fewer encounters and limited access to incoming material. Their histories unfold slowly, shaped more by internal processes than by mergers or external supply. The contrast between these environments highlights how strongly location influences outcome. Clusters like Abell 2029 represent one extreme, where interactions are frequent and accumulation dominates. Filaments offer a middle ground, providing steady flows without constant collisions. Voids mark the opposite end of the spectrum, where expansion and separation prevail. Together, these regions form a coherent whole. The universe does not distribute its material evenly, and galaxies respond accordingly. The immense size of IC 1101 reflects its long residence at a gravitational center, surrounded by countless opportunities to grow. The extended reach of Alcyoneus reflects sustained activity, supported by its position along a filament. Neither system can be understood in isolation. Their properties emerge from continuous interaction with their surroundings, shaped by forces acting on scales far larger than any single galaxy. The cosmic web supplies matter, defines pathways, and sets conditions that persist across billions of years. As attention moves outward from individual galaxies to this broader structure, scale begins to shift again. The giants discussed so far become nodes within an even larger pattern, one that extends beyond clusters and filaments into regions of increasing emptiness. This widening view does not conclude the story. Instead, it reframes it, placing the largest known galaxies within a dynamic landscape where growth depends on position, flow, and time. From here, the focus naturally drifts toward the forces that eventually limit such growth, shaping what can persist as the universe continues to expand and allowing the narrative to carry forward without pause. Across the vast span of cosmic history, the largest galaxies emerge not as sudden creations, but as outcomes shaped slowly by time, gravity, and position. Their origins trace back to an era when the universe was young, cooler, and far less structured than it appears today. After the initial expansion, matter spread outward almost uniformly, carrying only slight variations in density. These small irregularities mattered. Over time, gravity amplified them, drawing material inward with quiet persistence. For tens of millions of years, the universe remained dark, filled with neutral gas, and without visible sources of light. This interval, often called the cosmic dark ages, set the stage rather than the scene. Gradually, the densest regions began to change. Gas compressed and heated until the first stars ignited, marking the end of that early darkness. These stars did not appear in isolation. They formed within small groupings of matter, the earliest galaxies, each modest in mass and scale by later standards. Their light began to reshape the surrounding environment, altering how gas behaved and how future structures would grow. Within a few 100 million years, these early galaxies multiplied. Most were compact, irregular, and short-lived in their original form. Their importance lay not in their permanence, but in their role as building blocks. Over time, they interacted, merged, and reorganized, contributing material to progressively larger systems. This process unfolded hierarchically. Small galaxies combined to form intermediate ones, which later merged again under favorable conditions. There were no prefabricated giants waiting at the beginning. Instead, size accumulated through repetition. Each merger added stars, gas, and dark matter, slowly increasing mass while reshaping structure. Simulations of cosmic evolution show that this pattern was most active a few billion years after the beginning, when matter was denser and encounters were more frequent. As the universe expanded, distances grew, and mergers became less common. Growth continued, but at a slower pace, increasingly influenced by environment rather than proximity alone. IC 1101 fits naturally into this sequence. Rather than appearing as an anomaly, it represents an endpoint, the result of countless mergers unfolding within a dense cluster over billions of years. Much of its stellar mass likely assembled early, followed by a long period of relative stability. Star formation diminished as available gas was exhausted or heated beyond the point where it could condense again. Recent observations extend this picture further back in time. The James Webb Space Telescope has revealed galaxies in the early universe that already appear large, structured, and dominated by older stars, despite existing less than a few billion years after the beginning. These systems resemble smaller versions of present-day giant ellipticals, displaying maturity earlier than many models anticipated. Their presence suggests that, under certain conditions, galaxy growth can proceed with remarkable efficiency. Matter may accumulate more rapidly along dense filaments, or feedback processes may regulate star formation in ways that produce older stellar populations sooner. These observations do not overturn existing frameworks, but they encourage refinement, adjusting assumptions about timing and rate. Seen in this broader context, today's largest galaxies are not isolated curiosities. They are linked directly to these early systems. Connected through an unbroken sequence of growth and transformation, the universe builds complexity through continuity rather than leaps. Within this long timeline, IC 1101 and Alcyoneus follow different paths shaped by circumstance. IC 1101 appears to have gathered most of its mass several billion years ago, reaching a state where further growth occurred primarily through minor additions. Its stellar population aged, its internal gas remained hot, and its overall structure changed slowly. Alcyoneus reflects a different emphasis. While its host galaxy may not rival IC 1101 inches stellar mass, its central black hole entered a prolonged phase of activity at a later stage. For hundreds of millions of years, jets remained aligned and sustained, producing radio structures that continued expanding long after much of the surrounding universe had settled into quieter patterns. These timelines highlight that size alone does not define evolutionary stage. One galaxy may complete its primary growth early and persist as a massive, stable system. Another may express its influence through energetic processes that reshape space far beyond its visible form, even at comparatively later times. Both histories unfold within the same universe, governed by the same underlying forces. Gravity draws matter together. Expansion stretches space. Energy flows through matter in regulated ways, sometimes rapidly, sometimes slowly. Over billions of years, these processes produce a wide range of outcomes, from compact early galaxies to extended structures that challenge the limits of current understanding. What becomes clear is that no single snapshot captures the full story. Each observation reflects a moment along a long continuum. Light arriving today carries information from different eras, allowing reconstruction of growth through comparison rather than direct observation of change. The largest galaxies therefore stand as records rather than endpoints. Their mass, structure, and activity preserve the influence of early density variations, long-vanished mergers, and sustained interactions with their environments. They demonstrate what is possible when time and circumstance align over immense durations. As this historical view settles, attention begins to drift toward elements that are not directly visible. Beneath stars and gas lie dark matter structures that guided assembly from the beginning. Beyond gravity's reach, expansion accelerates, shaping what can continue to grow. These influences form the next layer of the story, extending the narrative outward without interruption into the forces that quietly set boundaries on cosmic structure. Seen from a distance, IC 1101 presents itself as a broad glow of starlight, extended and even, resting quietly at the center of its cluster. Yet this visible form accounts for only a small fraction of what the galaxy truly contains. Most of its substance does not shine, does not emit light of any kind, and does not appear directly in images. It reveals itself only through gravity, shaping motion and structure on scales far larger than the stars alone would allow. When astronomers estimate the total mass associated with IC 1101 and its immediate surroundings, the numbers rise to roughly 1,000,000 billion times the mass of the Sunday. This figure includes not only the stars within the galaxy, but also hot gas, diffuse material, and an overwhelming contribution from dark matter. Of this total, only a modest share belongs to ordinary matter, the kind that forms stars, planets, and visible structures. The stars themselves, numbering on the order of 100 trillion, account for a small fraction of the overall mass. Hot gas, detectable in X-rays, adds another portion. Together, these familiar components represent only a thin layer within a much larger gravitational system. The majority of the mass remains unseen, inferred through its influence rather than its appearance. This hidden component forms a vast halo of dark matter that surrounds IC 1101 and extends far beyond its luminous boundary. The halo stretches outward for hundreds of thousands, and likely millions, of light-years, its density highest near the center and decreasing gradually with distance. The visible galaxy sits within this halo, much like a bright region embedded in a far larger structure. In this arrangement, the stars mark only the inner portion of the system. The true extent of the galaxy, defined by gravity rather than light, reaches much farther. The dark matter halo determines how strongly IC 1101 binds its stars, how it interacts with neighboring galaxies, and how it responds to the surrounding cluster environment. This perspective changes how size is understood. Optical images suggest a boundary where starlight fades. Gravitational measurements reveal that the galaxy's influence continues well beyond that point. Motions of nearby galaxies, the behavior of intracluster gas, and subtle distortions of background light all trace the presence of mass where nothing is directly visible. The dark matter halo also shapes the galaxy's internal dynamics. It defines the depth and shape of the gravitational well in which stars move. Without this unseen mass, the observed motions would not remain stable over long periods. The galaxy would not hold together in its current form. Surrounding the bright central regions of IC 1101 is a faint stellar halo, composed of extremely old stars spread thinly across a vast volume. These stars are often low in heavy elements, indicating that they formed early, before repeated generations of stellar evolution enriched the environment. Their distribution suggests an origin tied to the gradual absorption of smaller galaxies over time. As IC 1101 grew within its cluster, many less massive systems passed too close to remain intact. Their stars were stripped and dispersed, becoming part of this extended halo. Rather than forming a compact structure, the halo preserves a diffuse record of past mergers, its stars following elongated orbits shaped by the galaxy's deep gravitational field. Within and around this halo lie thousands of globular clusters, dense groupings of stars that orbit the galaxy as coherent units. Each cluster contains hundreds of thousands, sometimes millions, of stars bound tightly together within a relatively small region. These clusters are among the oldest known stellar systems, having survived numerous interactions that reshaped the galaxy around them. Globular clusters serve as durable markers of history. Their ages, compositions, and motions reflect the conditions under which they formed and the paths they followed afterward. In a system as large as IC 1101, the sheer number of these clusters points to an extended and complex growth process, involving many contributors over billions of years. Taken together, the stellar halo and globular clusters illustrate that mass accumulation is not a smooth process. It leaves behind structure at many scales, from diffuse light spread across intergalactic space to compact remnants that persist unchanged for immense spans of time. The dominance of dark matter in this picture shifts the meaning of density as well. Despite its enormous total mass, IC 1101 remains extremely sparse when averaged across its full volume. Most of the space within the halo contains very little ordinary matter. Even the dark matter itself, though massive in total, is distributed thinly across vast distances. This low density allows such large systems to exist without collapsing inward or tearing themselves apart. Gravity operates gently across scale, shaping motion without forcing compactness. Structure arises from distribution rather than concentration. In this sense, IC 1101 is not a single object with a clear edge. It is a layered system, where visible stars trace only the inner regions of a much larger gravitational entity. The galaxy's identity depends on whether one follows light or follows mass. Each approach reveals a different boundary. Alcyoneus, though different in appearance, follows a similar principle. Its radio lobes extend far beyond the stars of its host galaxy, guided by magnetic fields and sustained by energy drawn from a central black hole. Yet beneath those structures lies another dark matter halo, anchoring the system within the cosmic web and shaping how it interacts with its environment. In both cases, the largest galaxies challenge simple definitions. They are not defined solely by starlight, nor by a single scale. They consist of overlapping components, each contributing to the whole in a different way. Stars illuminate only a small portion of what is present. Understanding these systems requires accepting that most of their substance remains unseen. Dark matter does not announce itself through brightness or form. It reveals itself through patience, through the careful tracing of motion and influence over time. As attention rests on these layered structures, the concept of a galaxy becomes less a visible shape and more a region of influence. What matters is not where the light ends, but where gravity fades into the larger background of the universe. From this perspective, IC 1101 and Alcyoneus appear less as isolated giants and more as dense knots within an extended field of matter. Their true size lies not only in their stars or radio lobes, but in the invisible mass that surrounds them, binding them to the larger structure of the cosmos, and carrying the narrative forward into questions of how such influence eventually meets its limits. Long after individual discoveries are absorbed into catalogs and comparisons settle into reference tables, a broader influence continues to shape everything discussed so far. It is not centered in any galaxy, nor anchored to any cluster. Instead, it operates everywhere at once, setting conditions that no structure can fully escape. This influence is known as dark energy, and its presence alters how size, distance, and connection unfold across the universe. Near the end of the 20th century, careful observations of distant supernovae revealed an unexpected pattern. Rather than slowing under gravity, the expansion of the universe appeared to be accelerating. Galaxies were not only moving apart, but doing so at an increasing rate. This behavior implied the existence of a pervasive component of energy, one that counteracts gravitational attraction on the largest scales. Dark energy does not clump or form structures of its own. It fills space uniformly, exerting its effect through expansion rather than pull. As the universe grows, its influence becomes more pronounced, gradually shaping the long-term behavior of matter across cosmic distances. One way to picture this process is through expansion itself. As space stretches, distances between large structures increase. Even when those structures remain internally bound, on small scales, gravity still dominates. Stars orbit within galaxies. Galaxies remain bound within clusters. But beyond a certain scale, expansion becomes the stronger influence, setting a natural boundary on how large connected structures can become. This boundary does not appear abruptly. Instead, it emerges gradually, as a balance between competing tendencies. Gravity draws matter together, encouraging growth. Expansion pulls space apart, discouraging long-range cohesion. Where these effects meet, limits begin to form. Simulations of cosmic evolution suggest that structures extending beyond a few tens of millions of light-years are increasingly uncommon. At those scales, expansion stretches space faster than gravity can compensate. Material that might otherwise remain connected drifts apart, thinning the outer regions of large systems. Placed within this context, Alcyoneus takes on added significance. Its radio lobes span roughly 16 million light-years, approaching the range where expansion begins to matter. The jets that formed them carried energy outward over long periods, yet even they operated within conditions set by the universe's overall growth. This does not imply that Alcyoneus is an anomaly demanding revision. Rather, it occupies a region near the upper edge of what current models comfortably allow. Its size becomes less a record to surpass and more a marker, indicating where physical processes begin to encounter broader cosmic constraints. If much larger radio structures were found, extending far beyond this range, they would invite closer examination. Such findings might suggest either particularly favorable environments or gaps in current understanding. For now, Alcyoneus appears to sit near a natural threshold, shaped as much by cosmic expansion as by internal energy. Dark energy also influences the future arrangement of galaxies and clusters. As expansion continues to accelerate, regions that are not gravitationally bound will drift beyond one another's observable reach. Over extremely long timescales, clusters like Abell 2029 will become increasingly isolated. Within such clusters, galaxies remain connected. Outside them, distances grow so large that light emitted beyond a certain point will never arrive. This creates an effective horizon, not as a barrier, but as a consequence of expansion itself. Beyond it, information simply fails to reach. In this distant future, the universe becomes quieter in structure. Clusters persist as self-contained systems, surrounded by expanding space. The cosmic web, once a connected network of filaments and nodes, gradually fragments into isolated regions, each carrying its own history forward. This process unfolds slowly, without disruption. There is no sudden transition, only a steady shift in scale. The era of frequent interactions and large-scale growth gives way to long periods of relative isolation, where existing structures evolve internally rather than through new connections. Over even longer spans of time, additional processes come into play. Within galaxies, gravitational interactions gradually redistribute energy. Stars are slowly scattered outward. Some escape entirely, drifting into intergalactic space. The process takes vast durations, far exceeding the age of the universe so far, but it continues nonetheless. Black holes, too, follow long trajectories. Although they appear stable on human timescales, theoretical work suggests that over extremely long intervals, they lose mass through faint radiation. This effect unfolds so slowly that it has no practical consequence for galaxies like IC 1101 today. Yet it sets a final boundary on persistence. These ideas extend the story outward, not in urgency, but in perspective. Even the largest structures discussed so far exist within a framework governed by expansion, energy balance, and time. Their growth, their present form, and their eventual transformation all reflect conditions established on the largest scales. Importantly, none of this diminishes the significance of the current era. Instead, it highlights it. The universe today supports large, complex structures, precisely because gravity and expansion remain in a particular balance. Galaxies can grow, jets can extend, clusters can assemble. IC 1101 and Alcyoneus occupy this window. Their existence reflects a period when matter still flows along filaments, when clusters still gather galaxies, and when energy released near black holes can imprint itself across intergalactic space. Observations of these systems show not only what has formed, but when such formation is most likely. The light reaching us carries information from times when the universe was slightly smaller, slightly denser, and more conducive to connection across large distances. In this sense, dark energy does not end the story of large structures. It frames it. It defines an era of growth and an era of separation. Without imposing sharp divisions between them, the largest galaxies become records of that balance, preserving evidence of what is possible under particular cosmic conditions. As attention rests on these limits, scale begins to shift once more. The focus moves away from maximum size and toward continuity across time. Structures appear less as fixed achievements and more as temporary configurations, shaped by forces acting steadily and without emphasis. From here, the narrative naturally softens. The largest galaxies no longer stand alone as extremes, but as participants in a broader process that includes expansion, delay, and observation itself. What remains visible is shaped not only by size, but by timing, distance, and the quiet movement of light through an expanding universe. Numbers invite reflection long before they invite conclusions. When attention turns toward IC 1101, with its immense population of stars, those numbers begin to open a space for wondering rather than answering. The scale alone reshapes how possibility is perceived, even before any assumptions are made about life itself. With an estimated total on the order of 100 trillion stars, IC 1101 contains more stellar systems than most galaxies combined. If each star hosts at least one planet, a conservative assumption by current standards, then the number of planets rises into the same range. Even when narrowed drastically, imagining that only a tiny fraction occupy conditions similar to those that allow liquid water, the remaining count still reaches into the tens or hundreds of billions. Such abundance does not guarantee outcomes. It simply establishes capacity. The sheer volume of potential environments exceeds the total number of humans who have ever lived on Earth by many orders of magnitude. From this perspective, IC 1101 represents not certainty, but an expansive field of opportunity, spread across an enormous volume of space and time. Time itself adds another dimension. The stars that dominate IC 1101 formed early, many billions of years ago. Long before Earth existed, these systems were already aging, orbiting quietly within the growing galaxy. On Earth, life required several billion years to progress from simple chemistry to complex organisms capable of reflection and technology. Against that benchmark, IC 1101 has offered comparable or longer spans to its planetary systems. If similar processes unfolded elsewhere, hypothetical civilizations could have had far more time than humanity has known. Entire histories could rise, transform, and fade, while the universe around them continued expanding. Compared to such intervals, the few 100,000 years of human existence appear brief, and the few thousand years of recorded history feel almost instantaneous. Yet scale introduces constraints as well as opportunity. IC 1101 is not compact. Its diameter stretches across millions of light years. Within such a structure, distance becomes a limiting factor. Signals do not travel faster than light, and even at that speed, crossing the galaxy requires millions of years. Communication across such distances would be marked by deep delays. A signal sent from one region would arrive in another after time spans long enough for planetary climates, ecosystems, and cultures to change beyond recognition. Any reply would carry an even greater delay, returning to a world that might no longer resemble the one that first transmitted the message. This temporal separation softens expectations. The absence of detected signals does not point cleanly toward absence of activity. It may simply reflect the difficulty of alignment, where distance, timing, and limited observation windows rarely coincide. Within structures as large as IC 1101, synchronization becomes an extraordinary challenge. Alcyoneus extends this perspective further. When its vast radio lobes are included, the scale grows larger still, even though those lobes are not sites of stars or planets. They underline how far influence and structure can stretch, and how long signals take to traverse them. Distance alone reshapes the meaning of connection. Within this context, the idea, often summarized as the Fermi paradox, takes on a quieter tone. The traditional framing emphasizes contrast between apparent opportunity and observed silence. Here, that contrast becomes less stark. Opportunity remains vast, but observation reveals only what lies within narrow bands of time and sensitivity. One way to imagine this limitation is through scale rather than expectation. Observing the universe is akin to illuminating a small region of a very large space for a very brief interval. What lies beyond that illuminated region remains unregistered, not absent, simply unobserved. Distance, timing, and orientation all matter. From this view, IC 1101 does not resolve questions about life elsewhere. It reframes them. The galaxy demonstrates how abundance and separation coexist. It shows that large numbers do not translate directly into visibility, and that absence of evidence carries many interpretations. The same physical principles that allow galaxies to grow to such scales also limit interaction within them. Light travel time preserves the past while withholding the present. Expansion separates regions, even as gravity binds them locally. Communication becomes subject to geometry as much as intention. In this way, the silence associated with distant galaxies can be understood as a natural outcome of structure rather than a puzzle demanding resolution. IC 1101 offers an environment rich in possibility, layered across billions of years, yet partitioned by distance and delay. The galaxy's vastness does not diminish the prospect of life, nor does it confirm it. It highlights the difference between capacity and contact. What unfolds within its countless systems may never intersect with what is observed elsewhere. Not because it is rare, but because space and time impose quiet boundaries. As attention drifts outward again, the focus moves away from individual outcomes and toward the broader pattern. Life, if it arises, does so within constraints shaped by scale. Communication, if it occurs, travels slowly across immense spans. Observation captures fragments of a much larger story. Within IC 1101, as within the universe as a whole, possibility expands faster than connection. The result is not emptiness, but separation, woven into the structure of space itself, and carried forward as the narrative continues, without conclusion, into the next widening view. Stepping back from the immense outlines of IC 1101 and Alcyoneus, the landscape of galaxies begins to widen again, revealing that scale alone is only one way the universe explores its possibilities. Across the observable cosmos, different systems occupy extreme positions along many other dimensions, each one highlighting a distinct path through cosmic history. One such example is UGC 2885, often referred to as the Rubin Galaxy. Unlike the giant ellipticals discussed earlier, this is a spiral galaxy, with sweeping arms that curve outward in a familiar pattern, yet on a scale far larger than what is typical. Its diameter stretches to several 100,000 light-years, and its stellar population is estimated to be many times that of the Milky Way. Despite this size, UGC 2885 retains a relatively orderly structure. Its spiral arms remain coherent, and its disk shows less disruption than might be expected. This suggests a calm evolutionary history, with fewer major mergers than galaxies of comparable mass. In this case, Largest does not imply violent growth, but rather sustained formation under stable conditions. Nearby, in conceptual space, though very different in appearance, lies M87. This galaxy does not hold records for overall size or star count, yet it occupies a unique place in astronomical awareness. At its center resides a supermassive black hole whose mass reaches several billion times that of the Sun. More notably, this black hole became the first to be imaged directly through the coordinated effort of the Event Horizon Telescope. The resulting image, a faint ring surrounding a dark center, offered a new way of seeing. M87 became emblematic not because it was the most extreme object of its kind, but because it was the one whose properties aligned best with available instruments. Its position, size, and relative proximity allowed theory to meet observation in a direct way. In this sense, records are sometimes set by circumstance rather than magnitude. A galaxy may become iconic not by exceeding all others, but by allowing itself to be measured with unusual clarity. M87's role highlights how technological reach shapes which cosmic features become familiar. Beyond these examples lies a wide spectrum of other galactic extremes. Some galaxies stand out for their extraordinary brightness, emitting as much energy as hundreds of trillions of suns combined. These luminous systems often derive their power from intense activity around central black holes, converting in falling matter into radiation across vast distances. Others are remarkable for their pace of star formation. In certain distant systems, stars are born at rates hundreds or thousands of times greater than in the Milky Way. Such galaxies appear briefly during periods of abundant fuel, rapidly transforming gas into starlight before quieter phases follow. At the opposite end of the scale are galaxies that barely register at all. Some contain only a few thousand stars, scattered thinly through space, and bound loosely by dark matter. These faint systems challenge detection, yet they provide insight into the minimum conditions required for a galaxy to persist. Isolation offers another form of extremity. A small number of galaxies reside far from any substantial neighbors, separated by tens or hundreds of millions of light-years. Their histories unfold with minimal interaction, shaped primarily by internal dynamics and the gradual expansion of the universe, rather than by encounters with others. Each of these cases illustrates that record holding can describe many different qualities. Brightness, star formation rate, isolation, and structure all define axes along which galaxies can become unusual. No single metric captures their diversity. One particularly striking departure from common forms is Hoag's object. This galaxy presents as a near-perfect ring of stars surrounding a sparse central region with little material in between. It lacks the spiral arms of disk galaxies and the smooth profile of ellipticals, standing apart from familiar categories. The origin of such a structure remains open to interpretation. Various formation scenarios have been proposed, involving resonance effects, past interactions, or internal dynamics, yet none fully account for its symmetry. Hoag's object persists as a reminder that not all galactic shapes fit neatly into established sequences. Taken together, these examples broaden the meaning of extremity. They show that the universe does not focus its variation along a single dimension. Instead, it explores a wide parameter space, producing systems that are unusually large, unusually bright, unusually quiet, or unusually shaped. This variety softens the idea of hierarchy. A galaxy that is not the largest may still reveal unique processes. One that does not shine intensely may still offer clues about dark matter or early formation. Extremes are distributed across characteristics rather than concentrated in one category. In this wider context, IC 1101 and Alcyoneus become part of a larger collection of reference points. They are not isolated curiosities, but members of a broader set of systems that test assumptions and refine models. As attention moves among these diverse examples, classification begins to feel provisional. Labels such as largest or brightest serve as temporary guides rather than final statements. They help organize observation while remaining open to revision as new data arrives. The universe appears comfortable with this openness. It continues forming galaxies under a range of conditions, allowing unusual outcomes to coexist with more typical ones. Each extreme adds texture to the overall picture, without demanding a single narrative. From here, the story does not narrow back to a single object. Instead, it remains dispersed across many forms, inviting a quieter appreciation of diversity itself. The record books expand, not toward closure, but toward an ever broader view of what galaxies can be, as the cosmic landscape continues unfolding beyond any single measure. Placed within the deepest stretches of time, galaxies like IC 1101 and Alcyoneus begin to look less like permanent fixtures and more like temporary arrangements, shaped by conditions that exist only for a while. Their immense size, their activity, and even their visibility belong to a particular era of the universe, one that unfolds between a distant beginning and an even more distant fading. In the nearer future, measured in billions and then trillions of years, change continues quietly. IC 1100. And one may still absorb a handful of smaller companions drifting through the Abell 2029 cluster. Yet, its ability to form new stars is already close to exhaustion. The bright, massive stars that once dominated such systems have long since vanished. What remains are smaller, longer-lived red stars, slowly consuming their fuel over extended spans of time. Alcyoneus follows a different path toward the same general outcome. The jets that once carried energy outward across millions of light-years do not persist indefinitely. Over hundreds of millions, perhaps a few billion years, the steady inflow of matter toward its central black hole diminishes. As fuel supply weakens, the jets fade. The vast radio lobes, no longer replenished, gradually disperse into the surrounding intergalactic medium, becoming harder to distinguish from the background. These transitions do not happen suddenly. They unfold over intervals so long that individual changes blur together. Galaxies that once dominated their surroundings slowly lose contrast against the broader universe, their most striking features becoming subdued remnants of earlier activity. Far beyond this stage lies an era when stars themselves become rare. After tens to hundreds of trillions of years, even the smallest stars exhaust their fuel. Nuclear fusion ceases as a widespread process. The universe becomes populated primarily by stellar remnants, white dwarfs cooling steadily, neutron stars drifting silently, and black holes carrying most of the remaining concentrated mass. Interactions still occur, though infrequently. On rare occasions, remnants pass close enough to influence one another, producing brief releases of energy. These moments, however, are isolated against a backdrop dominated by long intervals of little visible change. As time continues outward, black holes themselves enter a final phase of transformation. Through extremely slow emission predicted by quantum processes, they lose mass over extraordinary durations. For the most massive black holes, comparable to those found at the centers of galaxies like IC 1101, this process extends to timescales that dwarf all earlier cosmic history. Eventually, even these objects fade, leaving behind a universe composed largely of low-energy particles and diffuse radiation. Differences in temperature and structure diminish. Large-scale processes capable of producing complex change become increasingly rare. Viewed from this perspective, all large structures appear temporary. Stars, galaxies, radio lobes, and even black holes exist for finite intervals, shaped by a steady trend toward greater uniformity. The immense systems described earlier in this series are not exceptions to this pattern, they are expressions of it, unfolding during a period when matter still gathers into recognizable forms. Against such vast timelines, the present era stands out quietly. The cosmic web is fully developed, tracing filaments and clusters across enormous distances. Dark energy has begun to influence expansion, yet has not entirely separated structures from one another. Galaxies remain visible in great numbers, their light crossing space to reach observers. It is during this interval that objects like IC 1101 and Alcyoneus can be studied at all. Their stars are still luminous, their environments retain enough contrast to reveal structure. Their histories can be inferred from signals that have not yet faded into uniform background. In this sense, the present moment occupies a narrow window. It comes after sufficient time for complexity to arise, yet before the long dispersal that gradually erases large-scale features. Observations made now capture a universe that is still rich in form, still marked by interactions across many scales. The significance of this timing does not lie in privilege or permanence. It lies in opportunity. The universe, at this stage, offers enough information to reconstruct its story, to trace how matter assembled, how energy moved, and how structures grew beyond ordinary scales. IC 1101 and Alcyoneus serve as examples within that story. They test existing ideas, stretch definitions, and reveal how environment and time combine to shape extremes. Their existence does not resolve questions so much as frame them within a broader context of change. As attention drifts across these immense intervals, from near futures to far horizons of time, the sense of scale deepens once more. The largest galaxies ever found become chapters rather than conclusions, part of a sequence that continues beyond direct observation. From here, the narrative does not close. It remains open, able to return to earlier moments, earlier structures, and earlier questions. Each seen slightly differently when placed within the long arc of cosmic time, where the present quietly holds its place between what has already passed and what has yet to unfold. Throughout this journey, we have gently touched upon a vast yet tranquil idea. The universe does not display its greatness loudly. Its most immense structures do not arrive like a bolt of lightning, but reveal themselves gradually. As we widen our perspective, refine the way we listen, and accept that what we see is only part of a much larger story. Galaxies spanning millions of light years, faint radio lobes, and even the millions of years it takes light to cross a single structure all remind us that the scale of the universe is not only spatial, but also mnemonic. Every signal that reaches us is a whisper carried from a distant past. Thank you for taking the time to accompany this journey, to listen, and to let your thoughts drift slowly through those vast expanses. If this episode has offered you a moment of peace, or a gentle question to hold, remain with the channel. In the episodes ahead, we will continue exploring unexpected wonders and quiet, profound mysteries still waiting to be perceived within the immense universe, where even silence has a story of its own.